Welcome to the fourth lecture of Business Mathematics of the courses that is designed, as I have told you, by the University Grants Commission, and we are into the involvement of so many beautiful mathematics during the three lectures that we have had earlier. In this lecture very particularly, I would be describing, or we will be learning about a bit of total differential, very much similar to that we have done for calculus of single variable, and then we will be doing exclusively for partial derivatives, and that we will be having called as a chain rule. So we begin with something like this. As we started earlier, if we have a function u that we have designated as x and y, and further, now this is the new thing, and if x is any function of t and y also is another function of t, mind it, t is a variable, or in other words we can call t as a parameter, and so we will be having this. You may call as both of them may be called as parameters, or in other words they are nothing but variables. So to be very precise, in u is equal to fxy, we have x is a function of a single variable t, and we have the y also as a function of t, and we want to evaluate something as du dt. That is what we call earlier as total derivative. We have called it as total derivative. Now the main aim is that we want to classify them, the single calculus and the more variable calculus. So we will be having, as I have told you earlier, is written as something df upon dx into dx dt plus, that is df dy into dy dt. This is the first formula that we can have called as a total derivative, and one can observe, which we will be classifying later on, we will call it as equation 1. The partial derivatives involves in these two, and dx dt and dy dt, as you know, we call it as the total derivative. This dx upon dt and dy dt will be evaluated from these two equations, and the partial will be calculated from this equation. This is the first thing that I would like to do, and in the second what we have is, this is what we can designate as number 1 of today, is called as total differential. Is a very important relation that we have, and the second that we want to do, number 2, is called as chain rule. Even very important. Chain rule is completely the partial derivative, and we will be having more than one variable, as you can see, with a single variable. So again, starting with, if u happens to be a function of x and y, and this time note, and if x is a function of, similarly, phi, this time it is two variable t1, t2, y is also a function of t1, t2, then we apply the chain rule. I'll call it as equation 2, I'll call it as equation 3, let me name it as equation 4. 1, 2, 3, first is the formula that we have, second, third, fourth, as you can see, is having the two functions t1, t2 and t1, t2. Mind it, these t1 and t2, t1, t2 should be similar, and therefore we will be having the formula as du dx. There will be 4 set du dy, and then we will be having du dt1 and partial du dt 2. So, in all we will be having 1, 2, 3 and 4. Look at this, how we make it. We will be having du dt1 dx plus du partial dt2 dt2 dx. We will call it as equation 5, the first chain rule. Then we will be having du dt1 and this is dt1, very similar, y plus du dt2 and this will become dt2 dy. We will call it sixth equation. Remember, these are with respect to the main independent variable. Coming to next t1, t2, they are the parameters or they are the variables with which x and y are connected. So, we will be having it as du dx and dx dt1 plus we will be having du dy dy dt1. I'll call it equation 7. And here we have du dx dx dt2 because I am doing with respect to t2 and therefore du dy and this is dy dt2. That marks the end of all these formula with which we will be dealing today. In this lecture mainly what we are interested, the chain rule and the total derivative, but that will be more clear by taking some of the illustrative examples, and those illustrative examples we will verify as how we can do or how we can match with our knowledge of these formulae. So, if you look into these, it will be very easy for us to understand, and therefore, we have this example to cast. If so, we mark it for example 1 of today that we want to make because that will make it more easier for us to understand, more easy for us to solve the problems based on it. So, if we have u is equal to x to the power 5 y to the power 4, where look at this, where x is a single parameter related to t square and y is also a function of t, that is t cube. The question is what will be the value of du dt. We want to find du dt. This relation goes, and it is easy now for us to evaluate it simply putting the values. The first that I would like to draw your attention towards this question and the example that I have taken while solving this. U is a function of x and y, that is true, that is given as 1. X is a function of single parameter t, here also y is a single parameter t. So, that indicates that we are going to use the total derivative formula, and if it is more than 1 t1 t2, naturally we will be using the chain rule, as you can understand. So, we solve the problem. I will mark it as equation 1 for it. I will mark these two as this, I can take as equation 2 and then I can take it as equation 3. So, let me finding df dx, dx dt, partial y complete or a total derivative this. So, we start from 1. Number 1 implies, remember that u is a function of x and y because this whole, if you look into right from the beginning that we are doing, this is u is a function of more than one variable. Naturally, it indicates that we will be doing the partial derivatives, and so first will give me, if I am doing with respect to x, obviously needless to say that I will be keeping x constant, and so it will give me with respect to y if I take, and so it will give me 4 x to the power 5 y cube. Similarly, if I have partial with respect to x keeping y constant, this I'll get 5 times x to the power 4 y as it is power 4. So this is du dx and du dy, the same thing as df dx. You can a function of x and y, so it is written this way, because this formula as well can be written as du dx. So without raising any kind of a confusion, we can make it as simple as that, dy, and this will become total derivative dy upon dt. This is what we have. Let me mark it first, second, third. I'll call it as fourth equation. Then in continuation we can have this as fifth equation, this as sixth value, and further. Now dx dt and dy dt are to be evaluated from relation 2 and relation 3. So from relation 2, 2 implies plain derivative that we have done in earlier classes, dx upon dt. No question arises which variable is to be treated as a constant, because this is not a partial derivative. So we have dx dt, that is what is equal to t square, and so it becomes 2 times t, and dy dt, similarly we will be having 3 times t square. Let me call it seventh equation, let me call it eighth equation. Simply all these values are to be treated and substituted in this. So that is the substituted in this equation. I will write the equation again, but nonetheless the fourth equation is similar to what we have written here. So I'll be substituting 5, 6, 7 and 8 in the equation 4. So we write here, put equation 5 through 8th in equation 4, and we will be having this, that is what we are required to find. Du dt is equal to partial, I'll go from 5, from 6, so I'll be having 5 times x4 y4. This I have taken from 6th. Multiply dx dt. Dx dt is from 7, we will be having 2t. So this is from 7th equation. Plus we have du dy to be taken from 5th equation, and that is 4 times x to the power 5 y cube. This is from 5th equation, multiplied by dy dt is from 8th equation, that is 3t square. So simple, as you can understand, that we will be simply substituting it for these values. This 3t square is finally taken from equation 8. If I solve it, I'll be getting 5 to the 10, x to the power 4, y to the power 4, this is t, plus 12, x to the power 5, y to the power 3, and t square. Mind it, this is du dt that we have. The question is asked whether you are to find in complete x and y, or let this be the answer, meaning thereby that we will be finding x4, y4 and t, and this is x5, y cube and t square. As it is given to you, x is equal to t square and y is equal to t cube. So I can put the value of x and y both in terms of t, meaning thereby this is of course the answer, but in terms of x and y only. In that case, I'll have to substitute the values of t here by taking common, or simply by putting t and t square at this place. We take another example similar to which we have done earlier just now. Is again a total derivative, but this time look at the formula, that how we are using it. The question reads as this. This is example 2 that we have. This is example 2, and the question reads as, if u is a function of x square minus y square plus sine of yz. Mind it, this is u is a function of x, y, z. If we speak theoretically, as we are doing since previous lectures, this I mark as equation 1 in this case, and where we have, like we did earlier, where y is e to the power x, z is equal to log of x. This is y something as function of x, and z is also some function of x. This is what I am resembling it with the theoretical aspect of what we have done little early. Mind it, we do not have any x related to. So y and z are function of x, single variable, and you have been asked to find du upon dx. That is how we write. If this all, then calculate. So du upon dx is equal to partial dx. We will be having dx again with respect to dx plus du dy. We will be having total derivative dy upon dx, and then plus this will be partial with respect to z, and in this we will be having dz dx. Let me call it third equation. Look at this, dx over dx, because x is related to x itself. We do not have anything related to this particular. So we will be writing now, differentiating it. First I'll calculate partial and then I'll calculate the total. So partial, that means I'll be starting from equation 1, from 1 that we have, because you need to calculate. So we will be having partial du dx. This time we will be keeping y and z constant. So we will be having with respect to x, so it will be only 2x. I'll be having du dy partial. This will be required here, du dy partial, keeping x and z constant. I'll be writing here with respect to y, x and z are to be treated constant. So we have minus times 2y plus we have here as cos of y, z is to be taken out. The reason is we have done ddx, the fundamental formula. This we had sine of ax is to be written as a cos of ax. This is the basic formula that we have studied in differential calculus of one variable when we were solving it. So I will be finding du dz also. This time x and y are to be treated as constant. We don't need the relation now here. So in that case, du dz, keeping x and y constant, we will be again writing it cos of yz, and y is to be taken out. So let me make all these taken together as equation 4. This is also same as I have done here. So this is the partial derivatives that we have calculated. What we need is dy dx and dz dx. So these two equations from here. And now I can write that y is equal to e to the power x implies dy upon dx. Remember, we are not keeping anything constant because this is a total derivative. So this is e to the power x. And then we have dz dx. So we will have dz dx is equal to 1 upon x. And as you know, dx dx is equal to 1. Taking all into account as fifth equation, I'll now substitute in the final result, and that substitution follows very simple. That is, I am putting in equation 3 now. Equation 3 henceforth implies as du dx is equal to, this is partial du dx, so I will be taking here, this will become 2 times x dx dx, so this is 1 plus du dy partial, as you can know. So du dy partial is to be taken from here, and I will be having z cos of yz minus times 2 of y, and we have dy dx, so into dy dx is to be taken from this place, that is e to the power x plus partial du dz, that is y cos of yz multiplied by dz dx. Last result is 1 upon x. Very simple now. We arrange, we simplify and write in a most simplified way. So this finally becomes 2 times x plus e to the power x z cos of yz minus 2y plus 1 upon x into y cos of yz. This is the result that we have, and this we can call as solution of it. Very simple, that we have found the total derivative. Coming now to the chain rule. We take one example, finding chain rule first, and then we will be illustrating few more results, as we can see here. But before that, what we need is a very important exercise that I would like to illustrate, and a simple one as well. So we will be doing it in a fashion this way. So example 3. This we call as example 3. If we have z is equal to x square plus 2 times xy, and if x is equal to u cos of v and y is equal to u sine of v, you are to calculate or evaluate partial dz dv. What will be the value of it is the question that is raised. I compare it to the chain rule. This particular z is equal to is equivalent to something as xy, and then this particular thing x is, if I compare it what I have studied just now, will be that x is a function of uv, almost similar to x is a function of t1 t2, the formula that we did. And similarly, if I have here, I can call it y also is some function psi of u and v. As I have told you that if I want to have more than one variables, that means if u is a function of x and y, and if x and y both are functions of more than one variable, kind of t1 t2, then naturally the chain rule has to be applied. And so here the question is also asked in the similar fashion, and we understand that the chain rule is to be applied. So we write here, we write this way, finding partial dz dv is equal to partial dz dx dv plus partial dz dy into dy dv. For your reference, I mind here and I write that this is a chain rule that I am going to use. in chain rule I read all partial derivatives. So, I will be starting from z is equal to x square plus 2 times xy will imply I want dz dx and I want dz dy. So, I will be having dz dx keeping y constant. I will be having 2 times x plus 2 times y plus 2 times y because I am doing with respect to x will also imply that partial with respect to y keeping x constant, naturally this will become 0 and I will be having with respect to y. So, this will give me only x. With respect to y this will become 1 and 2x will remain 2x because that is to be treated as a constant. So, this is one part of the result. Now, we come to second, that is I want to find the partial derivative with respect to v and partial derivative also with respect to v. So, dx dv, I will be coming from here, x is equal to u cos of v will imply that dx dv keeping u constant, I can have keeping u constant. So, we will be having u and this will become sine of v with a negative. I have used the formula ddx of cos of x is equal to minus sine x. This is all that we have done in earlier classes, and dy dv also, but keeping u constant, that is from here y is equal to, so y with respect to v, u is to be treated constant and cos of v, that is with respect to v. I am using the formula ddx of sine of x is equal to cos of x. What we need now is a substitution purely, and that substitution has to be made in this chain rule formula. Therefore, what we have now is partial dv. I am substituting on the right hand side, dz dx is to be taken from here. I will make it 2 times x plus y. Then I have dx dv, I will take it from here. This will be minus u sine of v. Then we have plus this dz dy. I will borrow it from here and I will substitute 2 times x into dy dv is to be taken from here and I will get u cos v. This is to be taken as u cos v. As I have told you, mind it, we want to convert them in x and y purely. So, if we need this answer in terms of x and y, then the question, you go back to the question and we will be having that question related here, and so we can write it as right hand side will be 2 times x plus y. The question given to you is x is equal to u cos v. So, it is u sine v and it is u cos v. So, u sine v means minus of y, and I will be having plus 2 times x into u cos v, and you can write it x. So, the final answer is minus 2 times y x plus y plus 2 times x square. If you want to solve it little more, we can have it minus 2 times yx minus 2y square plus 2x square is the answer, this one. So, we have been able to follow as how we apply the chain rule and at what particular juncture should we use the total derivative.